Today we're going to talk about substitution in definite integrals. Remember that definite integrals are integrals in which there are the limits of integration here on the integral sign. And so we're actually going to be evaluating this integral with those numbers. So we're really finding the area under the curve as opposed to just a formula to find the area under the curve. So from this integral, we need to decide who u is going to be. So I want you to look here at tangent x times secant squared x. You could actually do this one of two ways, but what I'm thinking you're going to see is that tangent's derivative is secant squared, and that is sitting right there. And if you remember from last time, that makes determining who u is a lot easier. So let's make u tangent x. And then we would find the derivative of tangent, which is secant squared x dx. And that's right here. So we can replace secant squared dx with du, and we can replace tangent x with u. Now the difference here between definite integrals and indefinite integrals is that these limits are for x, and x is no longer in our integral. It's now u. So you can't leave these numbers on our new integral because they don't apply to u. They only apply to x. So here's one of the options of what we can do here. We can use our u substitution to find new limits of integration, but with respect to u instead of x. So if I take 0, that was supposed to be my lower limit of integration for x, and I put it in here for x, I'll get the new limit of integration for u, or the lower limit of integration for u. So tangent of 0 is 0. So this 0 is actually not going to change. But let's look at the upper limit of integration, the pi over 3. That's really an x value. So let's come over here to where we substituted, and we're putting in pi over 3 right here for x. What is tangent of pi over 3? Oh, who remembers from pre-calc? It's radical 3. So that's going to be our new upper limit of integration. So now we're going to integrate this u function, and that's going to be 1/2 u squared. I'm not going to have the plus c this time because I actually have limits of integration. So because I changed the limits of integration so that they were with respect to u as opposed to x, I will not have to substitute tangent x back in for u when I'm finished. I can just put these limits of integration in right now, and I'll just be done. So I'm going to leave this 1/2 all the way out front, and I'm going to substitute radical 3 in. And then I'll substitute 0 in. And remember, when I'm evaluating a definite integral, I substitute both the upper limit and the lower limit in, and then I subtract them. So this is going to be 1/2 times 3, or 3 over 2. What you could do, if you don't believe me, is you could type this original integral into your calculator and you could see what you get. But I'll bet you're going to get 3 over 2. Okay. Let's try another one. I need a new color here. There we go. Okay. Integral of 0 to 1 of x over x squared minus 4 dx. Okay, so now here's that big decision. Who do I make U? What do you think? I'm going with the denominator. Let's see. And you know what? If it doesn't work, we can always just try something else. So du equals 2x dx. So I see x dx over here in my integral right here, but I don't see a 2. So I'm going to move this 2 to the other side. So I have 1/2 du equals x dx. And so now I can substitute x dx with 1/2 du. I am going to put the 1/2 on the outside. X dx is getting replaced with 1/2 du. And my x squared minus 4, that's u, but this is in the denominator. So my new integral is really 1 over u. But now here we have this problem of the limits again. So instead of using these limits of integration, which are with respect to x, I'm going to find the new limits. So I'm going to take 0, I'm going to put it in here for x, right here, and I'm going to get -4. So now that's going to be my new lower limit of integration. I'm going to take the 1, and I'm going to put that in here, and that's going to give me -3. So now I have an integral that's ready to be evaluated, or antiderivatived. Okay. Who remembers what the integral of 1 over u is? Now, if you recall, we talked about this yesterday. It's ln of the absolute value of u. Well, you can see by these limits right here, that's definitely going to be needed because I have to put negative numbers in for x, and I can't have negative numbers inside an ln function. But that's what I have the bars for. So 1/2 ln absolute value of -3. You know, I'm going to keep this -1/2 all the way on the outside. And then minus ln of absolute value of -4. So that'll be 1/2 ln 3 minus ln 4. So now there's a little bit of algebra here to think about. If you remember from pre-calc or algebra 2, when you are subtracting logs of the same base, they can turn into a fraction all in one log. So these are completely equivalent forms. Not a big deal, but kind of a big deal if you're looking at multiple choice answers. Also remember that a coefficient in front of a log is the same as an exponent on the argument. That's what this thing is here, the argument. And of course, an exponent of 1/2 is really the square root of. I'm going much farther than I need to, but this is the kind of stuff they pull on you in the multiple choice. And that would be ln of radical 3 over 2. So all of these steps are equivalent. This here is equivalent to this, which is equivalent to that, which is equivalent to that, which is equivalent to this. Now, I can totally see the AP people putting any of these in as the multiple choice answers, so beware. Okay, so in summary, if you're using U substitution, you need to change your limits of integration so that they're in the U form instead of in the X form. And when you do that, you do not have to substitute the X's back in at the end as we did with indefinite integration. So you should now try the homework problems, and you can check them with my answers.